Okay, so now we'll tell you how to select the technique. And there are 6 parts. First, how to select the technique. Then we talk about 3 rules of validation and selecting the performance metric. Then we go into, after technique, we go into the metrics, and then we talk about some common metrics and so on and so forth. So there are 7 things that help you decide which technique to use. There are 3 techniques. First of all, there is a modeling, there is a simulation, and there is a measurement. Very first thing that help decide is the stage that the system is in. So if the system doesn't exist, you cannot do measurement for sure, right? So you have to stick with the first one. For the measurement, you need at least a prototype. If not the real system, you need a prototype. In the companies, generally they have first prototype, and then they have real product. Outside, people will just see the real product, but the company, the prototypes, you can basically start doing a measurement. So these two are, this one is out if it is a pre-prototype stage. So this can be done a post-prototype as well as in. So that one will limit your thing. Once you have done that, then how much time you have? If the answer is required in an hour, your boss called you and said, give me the answer, then you don't have time for measurement, right? So measurement time varies. Measurement time varies in the sense that depends, it could be 1 day, it could be 1 hour, it could be 1 month. The simulation time is, so this one is variable, but whereas the modeling time is small. Modeling time, if somebody asks me an answer, right away, then I can do the modeling right away and I can give the answer. And I can give the answer generally, as I said, by using my back of the napkin techniques, even right while we are sitting right there. So that is small. But simulations, we could take medium time. Tools. And what is it that we know, or what is it that we can do? So there are people who can do modeling, you need them. There are people who can do the writing of the programs. We need computer languages, simulation tools, and things like that. And for this, we need the instrumentation. If the instrumentation is not there, then measurement is out. If you don't have any simulation techniques or simulation systems, then that is probably out. And then if you don't know queuing theory or things like that, then analysis is out. Yeah.
So an evaluation technique, you said just one of these techniques. Shouldn't all of them be the actual technique?
Should all of them be used? Yeah, okay. Well, coming to that one in a minute as to how many of these you use. But this will help you rule out some of them.
Shouldn't I want all of them?
If you could, you want all of them, right? But the thing is, here the thing, you generally in the real life, you don't get to do all of them because first thing that really, here the thing, this is in the order actually. It is quite possible that you cannot do something because it doesn't exist. It's not your choice, it's just the time, right? Second thing is the time required. You don't have 3 months. We have to get the product out next month. Right? So while it is good to have all 3, but you may not be able to do all 3. So this will limit it to maybe 1 or 2. And then we will see next as to how many we need. Tools. So yeah, you may not have all the tools that you need. Accuracy. Analytical modeling gives you very low accuracy result. Okay? The modeling people think that they have the right answer, but that answer is really not, could be very much off. Measurement, we don't know really. It varies. A lot of people believe that the measurement is the real thing, but it may not be real thing, it could be buggy. And then simulation gives you somewhere between the two. Trade-offs evaluation. If you want to compare something, you want to change a parameter. What happens if I change this x to y to z to this and that? It's very easy to do with the modeling. With the model, you can plot a whole graph. With measurement, it needs a lot of time. But every time you do an experiment, a day is gone. With simulation, it is halfway between them. I mean, not halfway, in between them. Cost of the modeling is small, given that if assuming that the analysts don't charge you too much. Cost of measurement is high, right? Because you need the equipment and you need the time and to use all that equipment, right? And the simulation is medium. Sellability is whether the people will believe the results. Measurement is very high sellability. You just go to somebody and say, I measured the real system. No, it's not that, MM1 queuing model of this. This is a real system. We did the measurement, and this system worked twice as fast as that one. They will believe you much more, right? The sellability of the analytical result is low, and the simulation is medium. Yeah.
What do you mean by instrumentation?
Instrument.
In the field,
Tools. You need to be able to measure something. You need the instrument, right?
Okay, so this is not put in the code in the program to output.
It could be code in the program. It could be a hardware system. It could be a hardware monitor. Right? Yeah.
In using things like hardware monitors, do you feel that that would throw off the results because the hardware has its own parameters, its own factors, its own metrics that affect your...
So any instrumentation can throw off the result, including whether it is software or hardware. Generally, hardware actually throws off less, because hardware monitor would be external to the system, in the sense that it will not really be part of the system. It will be just monitoring it from outside, if you design it right. I mean, it is quite possible that you have to design it in the middle of the system, then it will affect the performance. Yeah.
So is it a good idea to kind of do these analytical modeling, simulation, and measurement kind of in order, like in the early parts of the design phase, analytical modeling is better, and then when you go a little bit further on, you can invest more time, simulation is better, and when you get to the end and you have to know for sure everything's good, measurements.
Okay,
so
good.
kind of
Yeah.
goals
Yeah.
over time.
That's the thing, you will probably not, again, in real world, there's not that much time. But if you are following up the product, and so you are, here's the thing, I grew up in a group whose full job, there were 20 people all doing performance analysis. All right? And so this is Digital Equipment Corporation. So they are designing all these computers and everything else, and our job is to do the analysis. So we stayed with the product for a long time. Right? So if that is the case, yes. First people who were doing it were the analysis people, and then it moved on to simulation people, and then moved on to measurement people. Okay? All right, but here you think, how many you need? I cannot trust the result of a simulation model until it has been validated by analytical modeling or measurement. So you cannot just do the simulation and say, sorry, here it is. Simulation results cannot be believed because you could have a bug in the simulation, you could have the wrong assumption, you could have anything, so you need to validate by analytical modeling or measurement. So you need to have at least one point, not the whole point, at least one point where you can say, well, I did measure this point, I did not measure that point, but I measured this point, and this is correct. So we are not totally far off. Or I did analytical modeling, back of the envelope calculation for this case, and this case simulation gives me the same result. All right, so you need the validation of the simulation. Do not trust the result of an analytical model until it has been validated by simulation model or measurements. Same thing applies to the analytical model. Why should I believe your MM1 queuing model? Right? I do not believe it until you can validate one point in that whole thing with simulation or measurement. And same thing for measurement. I do not believe the measurement until it has been validated by, because if it be very far off, you could have just had a bug, or you could have a wire off the track, you could have something wrong with the measurement, and so you have to have one point that you can explain. And people come up with some weird result which they say, I can't explain why this is happening. If you cannot explain it, then you really haven't done the work, because you have to be able to explain at least some part of it, and the other parts we can then believe. Right? So you need 2 out of 3. Right? Now, the difference is 2 out of 3 is that you cannot analytically model the whole workspace, but you can model at least some random point. You can say, well, if I assume single user, if I assume exponential arrival, then I can model it. You should simulate the same thing, single user, exponential arrival, you should get the same result. All right?